Janusz Makowsky from Technion on logics of finite Hankel rank.
Okay. Thanks a lot for willing to listen and for the invitation and for the atmosphere. And this talk is a variation of a talk I've given for Yuri's birthday. So there are a couple of people here who have heard it before. If I make mistakes, they can correct me. Okay, so I met Yuri 39 years ago. It's incredible. And happy to say this again. We stayed friends in spite of fertile disagreements sometimes.
A good way to put it.
Unfortunately, actually, in the original set, not in the published version, not in the slides, there were some unproven claims which we claimed that we were able to prove but didn't include in the paper, and some misprints. So I shall indicate in the talk where the problems are, and I would like to thank Moritz Müller from the Logic Group in Vienna, who reviewed the paper for Math Review and stumbled upon those things and was kind enough to inform us before. So the paper appeared in logics in the fields of logic computations as the second volume of birthday papers for Yuri, and it is also available if you are not in a library on archive. So what I'm going to do is I'm going first to discuss the Fefferman-Both theorem for finite structures, and I'll put it in an abstract setting. And actually I've been curious since the 80s when I worked in abstract model theory whether there is a characterization of a logic satisfies some kind of version of Fefferman-Both theorem if and only if it looks like this or like that. And we actually, in the chapter of the big fat book without an index, which nobody can read, on model theoretic logics, it's even asked as an open problem whether we can characterize logics with some kind of Fefferman-Both theorem. And then we have some new ideas on how to approach this, and I will spend some time in explaining this in detail. You don't have to get scared. It's about Hankel matrices. Now, Hankel matrices, if you Google them, you get thousands of papers in numeric analysis with plenty of applications everywhere. But this is a generalization of Hankel matrices to logic, not to numeric values, to structures. So we just took over the name because of the analogy. And at the end, I'll discuss some problems. So first, some notation. If you have a structure, tau structure, the product of two tau structure is the model theoretic Cartesian product. And actually, constants sometimes make problems, but we kind of brush over those problems. The sum of two tau structures is the model theoretic disjoint union. And generalized products are first order transductions, not necessarily first order, but for a practical purpose now, first order transductions of products. So you can redefine the predicates using first order formula. And generalized sums are scalar first order transduction of sums. The difference is that in products you can also say the new universe consists of triples of the old universe, and in scalar transductions you are not supposed to do this. We also look at K connections. Now, K connections, these were, and actually the Hankel matrices are called connection matrices in Lovász papers. So you have a graph with, say, 3 ports, 1, 2, 3, and you have another graph with 3 ports, 1, 2, 3. Then you can take the disjoint union, but identify those elements. And we denote this as disjoint union 3, or K, if there are K such ports. And these are called connections rather than disjoint unions, and they cannot, strictly speaking, be produced as transductions, but they behave in a very similar way. So these are K connections. And actually, in Lovász's paper, you can also have identifications which are more complicated, but I only deal with those. You could also say those 2 points are identified across something. Now, and then again, generalized connections are scalar first-order transductions of K connections. Now, the Fefferman-Watt theorem for finite structures, it just says that if you take any of those operations and you want to check a formula in the product or in the sum or generalized sum, then you can reduce this to checking many things in the components and then somehow piece them together using a Boolean function. I'll write down this precisely, and first thing we have to discuss is what are the logics on finite structures which satisfy some version of the Fefferman-Watt theorem. So if we do this strictly speaking, so let this be a generalized product on tau structures, then there is a T, a natural number, and a function rho, mapping formulas into strings of formulas with, let's say it's given like this, where K is a natural number, and a Boolean function. So the idea is that this is the formulas you check in the first structure, these are the formulas which you check in the second structure, and then you look at the results, you get zeros and ones, depending on whether the test is true or false. And then you plug in those zeros and ones into a Boolean formula, and you get 1 if and only if the product structure satisfies the formula and using the components. So
We're just talking about sentences, right?
at the moment I'm talking about sentences. You can extend this also to numeric parameters and all kinds of things, but here in this talk I talk only about sentences. Okay. And the formulas which you get to do this are called reduction formulas, and the important thing is that the number of tests you have to do doesn't depend on the size of the structure. So it's actually this was used in Courcell's theorem about checking in structures of bounded trees, because the structures can be decomposed, and then you can do some thing which people call dynamic programming to compute the value of the final structure by climbing up the tree decomposition. Now, the Fefferman-Watt theorem is also true for infinite structures and can also be stated for infinite products. But here we are only interested in the finite. And actually, the tricky part of the Fefferman-Watt theorem in the original 59 paper is indeed that if you take an infinite product, and then you have also to discuss what happens on the index set, but in the finite case, this trivializes. Now, the Fefferman-Watt theorem is also true for monadic second-order logic if you take sum-like structures rather than products. And this was certainly known already in the 50s. Maybe Dana can tell us about it. It turns out, I always, when I was a student, thought that Freisse was sitting in Algiers and Tarski was sitting here. But it turned out they were all visiting and discussing things together, and ultimately they presented a paper, but so saying that this happened independently is not quite true. It happened collaboratively somehow with several formulations of the theorem. The version for monadic second-order logic appears explicitly in Leuchli's 66 paper, which Schellach didn't read in detail, and so he reproved it in 79. And as far as I know, Yuri didn't understand the sketch Saharon gave, and then he wrote a paper figuring out the details, which is rather tedious. But all this is difficult because of the infinite case, not of the finite case. Actually, there is this parameter t. So if you have a formula of quantifier rank something q, then the reduction formulas may have an increased quantifier rank depending on the character of the generalized sum or product. Depends on the quantifier rank of the transduction. But if you just take normal sums or normal products, then T can be taken to be 0, and this is an important ingredient in the meta theorem. So anyhow, so we can reformulate now what happens in the monadic second order case. So now we have sum-like operations. Sum-like. Oops. There is something. Where is it? Maybe it should have been somewhere. Anyhow, sum-like generalized sums are arbitrary transductions of sums. And sum-like is if the transduction is quantifier free, to make sure that the T is 0. And then we can formulate, let be a sum-like operation on tau structures. Then again, there is a function and a producing reduction formulas and so on. But now, depending, no, this shouldn't have been sum-like. This should have been generalized sum. Then you get plus T. And if you take quantifier-free transduction, then you can take T equals 0. And this is the way it can be used for Courcell's theorem on model checking for monadic second-order logic. Now, indeed, there are many algorithmic uses. I have also written a long paper on this with new applications also, well, then new applications. MSL definable graph properties can be checked in linear time over graph classes of bounded tree width. And one way of proving it is just proving the Fefferman-Watt theorem and then doing the dynamic programming part. We also have, as a use of this, the MSL theory of graphs of bounded tree width is decidable by Zese. We have that MSL definable graph polynomials are computable in polynomial time over graph classes of bounded tree width, which I noticed first. If the class of tau structure has a decidable monadic second order theory, so does its closure under disjoint union, so you can play with this. And but in all these applications, T equals 0, at least for algorithmic parts, is essential. For decidability, it's not so essential. So if you want to do this into an abstract setting, then we have to see what we can do. Now, Lindström logic is just an abstract object where you have a set of formulas, but they are just names of something. And a set of structures and a satisfaction relation. And what I add additionally is I want some kind of a rank function. It doesn't have to be a quantifier rank, but it should be something which tells you how expensive it is to look at this formula. So in practical application, it was usually one used the quantifier rank, but in the open problems we'll discuss, you could have another option. If the set of sentences in the logic is uniformly computable, then we call it a Gurevich logic, motivated by his paper on the challenges. And the rho, the rank function, is nice if it holds that for a finite vocabulary there are up to logical equivalence only finitely many formulas of this quantifier rank, which happens to be true in the applications, but you can have a different rank function, and we'll see what we can do.
Do you require just that the syntax is computable?
No. Everything is computable, but you have to be able to decide who is a formula. I mean, if you...
Yes, definition what constitutes logic for t time, it's very essential that you have an effective compiler.
Yes. I was a bit shortcut here. Now, examples of nice logics in this sense is first order monadic second order logic, but also if you add the model or counting quantifiers, you get nice logics, where d, k, m, x, phi of x means there are exactly k elements modulo m satisfying phi. But here one has to be careful. This is why I show this example, is if you take the normal quantifier rank for this to be 1, I mean adding 1, then all of a sudden you get infinitely many formula of the same quantifier rank. But if you make it dependent on m, then you can satisfy it. So it happens to be nice. Now, indeed, these additional, there are 3 elements modulo 5 is expressible without the additional quantifiers, but then you have to write down first order quantification and to say that there is 1, 2, 3 which are not something. If you take them away, then you get something 0 modulo m. And so this is a bit tricky. To be nice, one has to adjust the definition of quantifier rank. So if you take this function rho 1, then it's not nice, and if you take rho 2, then it turns out to be nice for our purpose. Now, for an abstract framework, rho can be any function attaching some cost to formulas given as syntactic objects. In concrete examples, this is usually some variation of quantifier rank. But maybe if you want to do, I don't develop this now here into depth, but if you want to define abstractly what you mean by such a cost function, you probably would add a condition that it is weakly monotone with respect to subformulas. If psi is a subformula of phi, then the rank is equal than the rank of the big formula. And maybe Boolean combinations of formulas do not increase the cost. But I don't go into this now. Every abstract Lindström logic can be given a canonical syntax by adding generalized quantifiers for each definable class of structures. I mean, if you have an abstract logic and you just say for every similarity type, I introduce a generalized quantifier which says this is the logic, then you get some crazy syntax, but at least you can give it a crazy syntax like this. So in this sense, but then the question is how you define in this crazy syntax a quantifier rank such that the logic comes out nice. Now, I spoke before about translation schemes. So a translation scheme is just an interpretation, but I look at it as a transducer. You're given a structure, you have a sequence of formulas which define the interpretation, and you apply these formulas to the input structure, then the new relations are defined by these formulas, and you get a new structure, and then you only have some complicated or tedious conditions about the compatibility, how the arity of those formulas depends on the similarity type, and so on. But this is what we mean by a translation scheme. Now, this can be defined for any logic which has a notion of free variables. But in the applications, we usually, when we speak about sum-like, then these formulas have to be quantifier free. And if you speak of generalized sums, then we allow here also quantification. And the quantifier rank of a scheme is just the maximum of the quantifier ranks which appear in those formulas. Okay, so the translation of a formula is obtained. The structure is mapped into the new structures, and the translation of the formula is a backwards substitution, and you have a yes. Okay. So as a translation scheme is scalar if k equals 1, if the formula phi has doesn't increase the arity. So okay, so I said this already. So we have those operations, and sum-like and product-like, in contrast to generalized, just means quantifier rank is. And then we can reformulate what is the Pfefferman-Hond property, but you have seen it already twice, so I believe that you can read this afterwards yourself. Now, examples of logics that have the Pfefferman-Hond property is first order, and counting first order have it for product-like, and first order and monadic second order, and so on, have the property for sum-like. I forgot to say, so in the abstract definition, I want that the quantifier rank of the formulas you get is the same as the quantifier rank of the formula you want to check. For some operations, you have also first order and monadic second order logic together with counting. And the same is true also for connection-like operations. So here comes the question, what can we do to characterize logics which have the Fefferman property for some operation? Now, an operation is smooth if it has the property that if two pairs of structures satisfy pairwise the same LQ sentences, then applying the operation also satisfy the same LQ sentences. So now, if you have compactness, then we showed in the very old paper with Schellach that indeed the converse is true. Smoothness implies Fefferman-Watt, and Fefferman-Watt implies smooth. But in our context where we are here, this is a useless remark, and it doesn't seem to work in general. So here is an open problem. Find a natural example of a nice logic and an operation such that the operation is smooth, but it does not have the Fefferman-Watt property. I wasn't able to write down a convincing example. So here comes actually the important new part. Hankel matrices for properties. A property over a vocabulary tau is just a class of structure closed under isomorphism. And a Boolean Hankel matrix is the infinite matrix where columns and rows are labeled by finite structures. And inside the matrix, you compute the element, the element of the matrix labeled Aij is 1 if and only if the operation of those two structures happens to have the property. And the property has finite rank if the corresponding infinite matrix has finite rank over the field of two elements, or Boolean field. So you can also define an equivalence relation. Two rows naturally define an equivalence relation. The rows naturally define equivalence relation, where two structures are equivalent if they have identical rows. This can also be said in the following way. A is equivalent to B with respect to the property and the operation if for all sigma structures, if we allow changing of vocabulary, otherwise for tau structures we have that A combined with C is in phi if and only if B combined with C is in phi. And the property has finite index with respect to this operation if there are only finitely many equivalence classes. And it's easy to see that finite index is the same as finite rank. So these are just two ways of looking at it. And actually this is inspired by the narrowed Myhill theorem for words rather than structures. Now, why are those Hankel matrices important? Well, they play, or the connection matrices for connection operations play a very important role in the Lovász theory of graph limits and so on. But here is a theorem we proved in 2007. Let phi be a graph property such that the corresponding matrix has finite rank for the K connection. Then phi can be checked in polynomial time on structures of 3 with at most K. So this is actually a Kurzweil theorem which is logic free. It just says the only thing you have to know is that this Hankel matrix has finite rank for the K connection. Well, there is a lemma, then it has also finite rank for L connections L smaller than K, and then you can redo, but in a more complicated way, the dynamic programming argument, and this works. Now, I proved with my student Nadia a similar theorem for Clequist with a modified sum-like operation. And the important thing to note here is that there are uncountably many graph properties which have finite rank for a fixed operation. So this really shows, though the argument is a bit not cheating, it's true, but it depends on some indexing, but for every subset of natural numbers you do something. But it shows that but there are many more properties with finite rank than there are. So this is really a vast improvement on Courcelles' theorem. Now what we want to do is, for every definable property in a logic L, we say that L, if every property has finite rank for sums or products or connections, we say that L is a finite S rank, P rank, or so on. And what we proved with Tomer and Benny Godlin in 2008 is that if you have a nice fragment of second order logic and you have a smooth operation, then every definable property has finite rank. So that this really shows that there are many more cases where you can apply this theorem. As a consequence, we get that monadic second order and counting monadic second order logic have finite S rank and C rank, and additionally, if you take first order versions, then you have also finite product rank. Now the Pfefferman-Watt property implies finite rank. This is what is behind this proof. This is why we get to this connection. So we can formulate a theorem, let L be a nice Lindström logic and box a smooth operation, then any definable property has finite rank. And we can go on with this, and we get that if L has a Pfefferman-Watt property for all sum-like operations, then it has finite rank. And what is left is the following question: do we have a converse theorem which says that maybe in a way they're saying that every finite rank logic has an extension which satisfies the Pfefferman-Watt theorem. Now, finite rank alone doesn't help because there may be not all the formulas are there, so we have to find an additional condition, and we'll take a closer look. So a logic is, if it has a Pfefferman-Watt property, it has the additional property that every equivalence class in this of this having the same rows in the matrix is itself definable by a formula of the same complexity. So we can say a logic is box closed if this is true in general, and S closed, P closed if it is true for every sum-like, product-like operation. And the theorem says that a logic is if a logic is nice and has the Pfefferman-Watt property for all sum-like operations, it is S closed. So this is a hint that maybe we hit the right property. And the main theorem I want to present today, and this is a corrected version of it's only a misprint in the paper of theorem 16 in the birthday paper. Let L be a nice S-closed logic, then the following are equivalent. L has the Pfefferman-Watt property for every sum-like operation. All sum-like operations are smooth. For all phi and every sum-like operation, the rank of phi is finite, and for all phi and every sum-like operation, the index is finite, and the same holds for products and connections. So this is the story I wanted to tell, and then there are some open problems which we can look, or you can look at afterwards. Do I have?
Like a minute, maybe.
Okay, the main open problem is there a logic whose definable properties are exactly the ones of finite rank, and what you can try to do is just say take your logic, take all the things which are definable, and add them as generalized quantifiers. But it's not clear how you have to define the rank function to make everything work. So this is what we overlooked in the paper. We thought somehow we had a definition of this rank function which doesn't work. So Okay, this is basically what I have to say. Here is still a proof that there are many more classes of structures which have finite rank for a fixed operation, but it's not clear that you have that many classes of structure which have finite rank for every operation.
Thank you very much. Question for Janos? Sitting down. Well, thank you again.